conditions for perfect recall in associative memory. Actually, after going through the condition for perfect recall, I am going to tell you about the next topic that we are going to cover, that is about the statistical aspect of learning. Okay, so that will in fact complete the chapter on the learning processes. So let us try to recollect what we were doing in the last class. So as you remember that we had an estimated memory matrix M cap, okay, which was in fact realized out of the correlation in the way that we had considered that M matrix to be the outer product of Yk and Xk transpose. And then what we did was that we had fed pattern Xj. We had just happened to pick up a particular pattern X of j, okay, and then we got the output Y, okay, as the product of this M matrix and Xj vector. Okay. Now, what we are expecting out of this is that Y is equal to Yj vector, and let us see that what we obtained in the process. So what we did was just to apply the definition of this M matrix, this M cap matrix, the way we defined it as the outer product. So by replacing this with the outer product of the vectors Yk and Xk transpose, and then we just associated this Xk transpose with Xj, and this is what we had got as the summation of Xk transpose Xj times Yk, and this was from k is equal to 1 to m, which we had split up into the j term and the summation of all the non-j term. I mean k is equal to k not equal to j and k equal to 1 to m we took as one side, and on the other, I mean out of this summation we had taken out the case where k is equal to j. So that from this expression we were obtaining, by substituting k is equal to j, we were obtaining Xj transpose Xj times Yj, all vectors mind you, plus the summation term of this one remaining as it is, except for the fact that here we are summing up for k not equal to j, for k is equal to 1 to m, right. And we had, in order to simplify, we had furthermore assumed that all these vectors, they are having unit energy, so that the norm of all these vectors will be equal to 1. In other words, if we calculate the Ek of the kth, I mean of any vector, let us say the kth vector, then Ek will be equal to summation of xkl square, L is equal to 1 to m, and we just add it up and it becomes equal to 1. All right. So now what we can simply do is that we can write down that Y is equal to Yj plus this term, right. So let us see that what it becomes. We have already obtained that Y is equal to Yj plus this term, which is for k is equal to 1 to m and k not equal to j, xk transpose vector and xj vector, the product of these two, times yk vector. Okay. So this is the relation. Now this one is very simple. This is our desired term, okay, and this is the term that contributes to noise. And if we are talking in terms of the conditions for perfect recall, then what we need to do is that this term should ultimately be equated to 0, right. So let us see that what conditions are we getting for that. let us now see that okay. So, now let us represent this as y vector equal to yj, the desired vector, plus the noise, again in the form of vector we can write vj vector, because this after all is this xk transpose xj, this being the dot product that leads to a scalar quantity times yk. Okay. So, in other words, this becomes an addition of vector, so it is a vector. So, again I mean m dimensional vector this one will be. So, here if we write this expression by yj plus vj vector, then vj vector, which is nothing but the noise vector, will be summation k equal to 1 to m, k not equal to j, xk transpose vector xj vector, okay, times yk, that is to say this term. All right. Now, we can define the cosine of the angle between two vectors xk and xj as follows. Okay. Let us remember this expression. Okay. So, we can call this as equation number 1 and call this to be equation number 2. Okay, that is with reference to today only I am talking. Okay, maybe that I have given some equation numbers already, so let us not count on that. So, if I take these two equations, and then we can also define the cosine of the angle between two vectors xk and xj. Okay. And how is that defined? That is defined as xk transpose times xj, okay, and in the denominator we will be having the norm of xk times the norm of xj. All right. Now, what can we say about this? Now, certainly, since we are taking each of the unit vector, each of the applied vectors to be of unit energy, so that is why according to that assumption we are having norm of xk vector, okay, which is equal to nothing but the xk transpose dot xk, okay, which is equal to the energy ek. In this case, in fact, it will be ek to the power half, okay, and this is equal to 1, okay, by our definition. I mean, by what we are assuming of, I mean, of this one having unit energy. So, therefore, we are getting cosine of xk comma, sorry, cosine of xk comma xj, okay, that we are getting simply by the numerator term, that is xk transpose xj vector, right. Now, can you tell me that what is then the condition of the perfect recall according to this? The exactly so. Thank you very much for the correct answer. In fact, here what happens is that xk and the xj vectors cosine, that is what we are defining over here, and the cosine has to be 0. In other words, if the cosine is 0, that means to say that xk vector and xj vector, they are orthogonal to each other. Okay. So, if the key vectors are orthogonal, in fact, this x vectors, okay, we are calling as the key vectors. Okay. So, if the key vectors are orthogonal, in that case we can certainly write cosine of xk comma xj, that is equal to 0 for k is not equal to j. Okay. And in such a case, we are seeing that the term Vj becomes equal to 0, and I mean why is Vj becoming equal to 0? Because you simply see that if this term is equal to 0, then xk transpose xj, this term is also equal to 0, and if this term is equal to 0, then Vj vector is equal to 0, and Vj equal to 0 means y is equal to yj. I mean, it's a perfect recall. So now, I mean, that means to say that the condition that we are getting for the memory, for the associative memory to work perfectly, is that the condition is that the key vectors form an orthonormal set. So that is what we can say as the condition for perfect recall. So what is the key vector forming an orthonormal set condition? I mean, just to written in terms of mathematics, it is equal to 1 for k is equal to j, and this is equal to 0 for k not equal to j. Now, another aspect that we should have in mind is that the largest number of pattern that can be reliably stored to the matrix M cap. Now, you remember that in the matrix M cap, okay, we are storing pattern. In what form are we storing? In the form of associations simply, the yk and the xk, okay, taking them as the association, we were forming this matrix. Xk, yes, absolutely correct. Xk transpose, yes, thank you very much for the correction, that it should be xk transpose xj, which is equal to unity for k not equal to j and equal to 0 for k not equal I mean, this one is equal to 1 for k equal to j and equal to 0 for k not equal to j case. And now for the matrix M cap, okay, the largest number of patterns that can be stored in fact is given by the largest number of patterns that can be reliably stored in fact is given by the rank of the matrix M. So, this is given by the rank of the matrix M. So, let us remember this. Okay. It has been shown analytically, and we are not going into the derivation of that. All right. Now, this matrix M, in fact, okay, we can say that this is a matrix of dimension, let us say matrix of dimensions L by M. Okay. I mean, there is no harm in assuming this to be a rectangular matrix. If we assume it to be a rectangular matrix, okay, then the rank means what? It is defined as the number of independent rows or columns of the matrix, right? So, the number of independent rows and columns must necessarily be less than the minimum of L and M. Okay. So, that is why if R is the rank of the matrix, if R is the rank of the matrix, then we must necessarily have R to be less than or equal to minimum of L comma M. Is that all right? So, that is what we can have as the maximum number of patterns that can be stored. So, for a reliable recall, we must be having the number of patterns to be equal to or less than or equal to this R, okay, which necessarily will be given by the minimum of this L and M. Okay. I mean, should be less than or equal to minimum of this L and M. So, this aspect we must keep in mind. And now, although we have already established the condition of the perfect recall, the question that should come to our mind is that, is it that this condition is fulfilled by all the with all the real life cases? In fact, they are not. Okay. Many of the real life associations that we will be having, okay, there the key vectors do not necessarily form an orthogonal set. And I think from the mathematical analysis that we have already carried out, okay, we can emphatically say that if they are not orthogonal, then there is going to be some error in the recall. Okay. And let us see that the error in what form that we are getting. Okay. Now, let us consider a set of key patterns. Okay. So, we can define the set of key patterns as a set of x key vectors, which is nothing but consisting of x1 vector, x2 vector, etc., up to xq vector. Okay. And we are having the memorized patterns y mem vector as y1 vector, y2 vector, up to yq vector, the corresponding. Now, if we have this type of a situation that we have xk transpose dot product with xj transpose, okay. No, sorry, xk transpose dot product with xj vector. Okay. So, this one we had assumed to be 0, when there was a perfect recall. But if we now say that this is greater than or equal to some gamma, okay, for k not equal to j. Okay. That means to say, what is gamma? Gamma is the some lower bound. Okay. Gamma is the lower bound on this product xk transpose xj. Okay. So, if the lower bound gamma is large enough, in that case, what can we expect out of that? Okay. In that case, the response that we will get, okay, from the response y that we will be getting by feeding any of the key patterns is some response which will not be there in any of this y1 to yq's, isn't it? If we have the deviation of this to be quite high, if the lower bound of this is quite high already, that means to say that it is in no way, it is far deviated from the perfect recall case, then we are not going to find the response in this. Okay. So, this leads to the error. And another thing that we should keep in mind is that we are picking up the x vector, okay, during the testing. I mean to say, we are picking up the x vector from this key vector set. Okay. Let us say that we happen to pick up the xj vector. Okay. Now, xj vector may be represented in this form, that xj vector could be, in a stochastic sense, I mean to say, that xj vector may be written as x naught vector plus a v vector, okay, where v vector is a stochastic vector. So, v is a stochastic vector. So, if that is the case, that your pattern itself is a stochastic pattern, okay, meaning that it is having one x0 component, okay, and a stochastic component which is the v vector. Okay. In that case, we will be able to associate, okay, the x naught vector with y naught vector. So, x naught y naught, that will form a pair. Actually, what is y naught? Y naught is nothing but the corresponding response to x naught. So, x naught y naught, that will denote a pair of patterns never seen, denote a pair of patterns. In fact, why we are calling as never seen? Because it is not there in this set. X naught is not there in this set, Y naught is not there in this set, but we will be getting an association of X naught with Y naught. Okay. So, this is what we have to remember about the pattern association and the recall condition. Okay. I think the condition of perfect recall is something that we must understand, because the rest definitely follows logically from here. All right. So, before we go over to the next aspect, that is the statistical aspect of learning, is there any doubts that comes to your mind at this stage? Shall we then proceed to the statistical aspect of learning? Yes, please. Just a minute. I will get back to your question. Yes, what is your question?
Sir, xk is a set of all input vectors you could imagine which are being given to this system.
Correct. Xk is the set of, no, x key is the set. X key is the set of vectors that we are feeding, and that is consisting of x1 vector, x2 vector up to xq vectors, right?
We take a dot product with xj, that is one particular pattern of input.
Right. See, this is only one instance. Okay. Now, you see that when I put forward this condition xk transpose xj, okay, that means to say that take any key and take any g. Okay. The condition that you have is with k not equal to j. So, this should be valid for all combinations of k and g. Okay. And we only talked about a lower bound of this one in the earlier case, and in the first case we were talking of this condition. I mean, when we were talking of this condition xk transpose j, that means to say that we have considered that for all the combinations of k and j we have this condition fulfilled. Because you see, only when all these are fulfilled, then only you are going to get a perfect recall. Why? Because you just see this expression k is equal to 1 to m we are already taking. That means to say that this orthogonality condition must be valid for all. Is it clear?
xj is not some particular set, it's not necessary to be a subset of
xj, both xj and xk belong to the key set x key. Both of them, I mean, belong to, I mean, we just pick up any two and then show that they are orthogonal for the condition of perfect recall. They are all belonging to this set. Okay. And we are getting the recall error, that is an association of x naught and y naught which are not there in the set only when there is an error condition, only when the orthogonality conditions are not fulfilled. Followed that? Any other doubts?
What was the reason of you taking q to be equal to n in the last class? Just for mathematical.
Okay. Okay. I mean, the question is that why did we take q? I mean, why did we take m instead of taking q? Because we were taking q patterns, but m was the number of inputs. Okay. Simply to see that we do not exceed m, because ultimately the maximum storage capacity is restricted to the rank of the matrix M, and the rank of the matrix is given by L by M, or in our particular case where we had assumed the matrix to be a square matrix, we took L is equal to M. So, M in other words was the dimensionality of the matrix. So, anyway you cannot exceed the total number of patterns Q, okay, to be more than that of M. All right. So, that leads to, I mean, anything that is more than m number of patterns, anything that exceeds the rank of the matrix is something that we cannot recall. I mean, that is the maximum amount of storage that is possible. Okay. If you exceed that, okay,
So if I had a Q by N matrix where Q is greater than N, but I still had all the vectors that are also available.
if you have Q by M matrix, that's not possible. Yeah. So let us now go over to the statistical aspect of learning. In fact, in the statistical aspect of learning, okay, the focus that we are going to have is on the deviation between a target function f of x, okay, deviation between the target function f of x. In fact, we will be taking f of x vector. Again, x vector that denotes the input signal. Okay. So, what is f of x vector? Simply a function, okay, simply the regression function. So, in fact, if we have x vector to be the input signal and we have y vector to be the y to be the desired response, okay, in that case we can map this x to y by a function f of x, isn't it? So, f of x vector is defined to be the target function, and how we are achieving that function? We are not exactly realizing that function. We are only using a neural network, and that neural network, in that what are we doing? We are feeding a set of inputs, that is again the x vector we are feeding as the input to that x vector, okay, and we are realizing an actual function. So, we are interested now in finding out the deviation between the target function, which is f of x, and the actual function which is going to be f of x vector comma w vector, okay, which is realized by the neural network. Followed. So, again I repeat what it is: x vector the input signal, f of x vector, okay, that is the target function, what you can describe mathematically, but you are realizing the target function or a very close approximation to the target function by actually working through a neural network, where the neural network does a mapping, okay, from this x vector to the output. Okay. In fact, output could be a vector or a scalar, anything. Okay. Then that mapping function that the neural network is realizing, that will be a function of x vector as well as the w vector, the weight matrix, okay, weight vector or weight matrix, whatever way it is. So, this is what we are focusing upon in the statistical aspect of learning. Mind you, here we are not exactly considering the evolution of the weights w, which we were considering earlier, but here we are only interested about finding the deviation between the target function and the actual function. So, our focus is on the function level, mind you. Now, what is after all a neural network? Now, we are having a set of observations, all right. We are doing an experiment, okay, and we are not knowing, we are not exactly knowledgeable about the mathematical form of the function, but we have set up some experiment, okay, and we are having a set of observations out of that experiment, all right, and we are only gathering. So, that means to say that the knowledge that we are acquiring out of this is only an empirical knowledge, And how are we representing that empirical knowledge? That empirical knowledge we are representing by a set of training samples. Okay. Now, in fact, to say that we are defining x vector to be a input signal. Now, we can say that, I mean, we can denote it by a capital X vector, which is nothing but a random vector, as a random variable vector, okay, where each of these, where the instances of that vector is this x vectors, or rather to say xi vectors. Okay. So, I can define a random vector x vector, okay, whose instances are all the xi vectors, okay, and I can just happen to pick up n such instances of the random vector. So, I get a set of xi vectors for I is equal to 1 to n, meaning what? Meaning again x vector is a random vector and I am taking its particular instance xi. Xi is the ith instance of the vector, and how many such instances have I gathered? I is equal to 1 to n. So, the entire input, okay, the input is now being modeled as a variable. Okay. In fact, I mean to say that if x vector is defined as a random variable, this x vector is defined as a random variable, in that case what we are taking is just nothing but a subset of that random variable. So, we have only fed a limited number of instances, I is equal to 1 to n, okay. And also we are defining a random scalar, I mean output if we assume to be a scalar, okay. Let us say that the output, or rather to say we define a random scalar. So, D is nothing but a random scalar quantity, and this random scalar quantity we are defining as the set of DIs, where DI is the ith instance of that scalar, okay. I is equal to 1 to n. So, that means to say what? That we have got a set of training samples given by xi vector comma di, okay, for I is equal to 1 to n, and this realization that constitutes a set of training samples. So, the set of training samples we denote by T is equal to a set of xi vector comma di, okay, and we can have it as I is equal to 1 to n, okay. This set is the set T that we can consider, okay. Now, again what we are doing, I mean let me come back to the discussion that I was doing a little while back, that after all in a neural network what are we doing? We are actually gathering the empirical knowledge, and that empirical knowledge we are storing in the form of the training samples, okay. So, now these training samples, after all, finally what these training samples, how do we represent the training samples, or rather how do we encode those training samples? Those training samples will be ultimately encoded by the set of weight vectors, okay. But we will come to that later on, okay. Now, our idea is to find out the deviation between these two. So, we must have a good knowledge about f(x) and this f of x comma w, okay. So, let us first take this f(x) thing, okay, that what do we see out of this, okay. So, for this we can have a model like this, where the dependent, okay, I mean what did we take again? We had taken x vector to be a random variable. So, this is a random variable vector and this is a random variable scalar, okay. and what more we have to take is that this x vector is an independent random variable, whereas this d what we are getting is a dependent random scalar quantity. D is dependent and x is independent. Okay. We must have that in mind. So, D is dependent on x actually, because in our case, okay, what happens is that D is very much dependent on x. So, x is the independent and D is the dependent. So, the dependence between D and x, that can be modeled as f of x vector plus epsilon, where epsilon is the random expectational error, where epsilon is a random expectational error. Okay. And this we can simply depict as follows, that here x vector is the input, and then we are having a function, this f x vector function, and what we are getting, this f of x vector which we are getting as the output of this block, that is getting added to. So, here we will be having a summer and we will be adding the random expectational error epsilon to it, okay, and then we will be getting the D as the output. Okay. So, this in fact is called as the regressive model. It is a mathematical regressive model, that if we have, I mean what we have as the input is x and what we have as the output is D, and in between it is this function f x which models this. Okay.
So is this f same as the target function f?
Yes, yes. In this case, this f is nothing but the target function. Okay. So, this is the mathematical model, okay, in the form of a regression. So, this is definitely the target, okay, and we are having just a random expectational error added to it. Okay. Now, this regressive model that we have presented, that has got two useful properties. So, properties of the regressive model. The first property is that the mean expectational error given any realization of x vector is 0. So, mean of expectational error, that means to say what? Expectation of epsilon. Epsilon is the expectational error, all right. So, epsilon is the expectational error. So, mean of this expectational error, okay, given what? Any realization of the x vector. Okay. So, given any realization of the x vector, okay, and what is it going to be? This will be equal to 0. That is the first property of the regressive model, that is mean of the expectational error epsilon given any realization x vector is equal to 0. And as a corollary to that, okay, we can have, I mean, by simply applying this definition, that D is equal to f of x vector plus epsilon. Okay. So, if we take the expectation of this, okay, on the left hand side and right hand side, okay, then what it leads to is that f x vector, okay, that is equal to expectation of D given x vector. Quite understandable, isn't it? Because what happens is that we are taking expectation of D given x vector. So, that means to say what? Expectation of D given x vector will be equal to f x plus expectation of epsilon given x vector, and expectation of epsilon given x vector is already equal to 0. So, that is why this will be equal to expectation of d given x vector. Okay. And the second interesting property is that the expectational error is uncorrelated with the function fx. So, that means to say what? That expectation error is the expectational error epsilon, okay, that is uncorrelated with the function fx. Okay. So, that means to say that expectation of epsilon fx vector is equal to 0. Okay. In fact, it is quite easy to see that. Okay. This you can simply see like this. This expectation of epsilon fx vector, okay, that will be, actually we can write it as expectation of epsilon fx vector given a realization x vector. Okay. Just this epsilon fx vector definition itself will say that this can be realized as expectation of this. Okay. So, this square bracket is for this expectation and outside we have this one. So, this means to say what? That this means to say that this is becoming I mean f x vector goes out of the expectation operator, and on the inside we will be having expectation of epsilon given x vector. Okay. And this quantity we know is already equal to 0. So, that means to say that this is equal to 0. So, the expectational error is uncorrelated with respect to the regression function fx. Okay. So, this is the property of the regressive model. Now, this is the regressive model. Okay. Now, we are not getting this. We are not getting this function fx. We should have got that, okay, or rather the exact mathematical model of this is fx, but instead of getting that fx, we have got a neural network to do our job. Okay. And the neural network in fact is realizing a function f, which is a function of x vector as well as the weight functions w. And what we are doing? We are adjusting the w in accordance with what? In accordance with the deviation that we are getting between the target output or the desired output and the actual output. Okay. Now, we are already fed with the training pattern xi comma d, xi being the instances of the random variable x vector and d being the and di being the corresponding desired response of that. So, we already know that what the di's are. So, what we simply have to do is just to take the difference between the actual output from the neural network and the desired response, that is di, okay, take the error of that, and in turn that error is going to update the weights, that is w. So, just giving pictorially the neural network model that we are having as an approximation to this regressive model. So, this being the regressive model, the neural network that approximates the regressive model can be shown as follows. Here too the input will be the x vector, then we are going to have the function, the neural network function represented as f of x as well as w, right, and here y is going to be the actual output, okay, and d is going to be the desired output. So, plus this as minus, and this is the error, and we are going to pictorially show it as follows. Okay. The way of showing this invariably indicates that we are going to adjust this weights w vector in accordance with this error e. Okay. Now, what it means that here the empirical knowledge is represented ultimately is encoded by this weight vector W. Okay. So, what we can say is that, as if to say that the training samples or the training set T that you are feeding, I defined it earlier, you remember. So, this T is nothing but the training set, okay, for I is equal to 1 to n xi comma di. So, this training set T in fact in this case is mapped into the weight vector. Okay. That is what we are doing by the process of learning in the neural network. Okay. And let the actual response be y. Okay. Let the actual response be y. Okay. So that we have y is equal to f of x vector comma w vector. Okay. Now, we are having already d to be the desired response. So, we can calculate the deviation between the desired and the actual, and in fact, I think we did in our first 1 or 2 lectures only that we had in fact found out the sum of the squared errors. Okay. So, what we have to do is that we are defining a cost function C, which is to be expressed as a function of the weight matrix only. So, C as a function of W will be written as half also you remember that it is only for from mathematical convenience that we have been using this half, okay, and summation of what di minus f of xi vector comma w, okay, and squared of this. That means to say what? That the sum of all the squared errors, and sum computed over what? What is the limit of the summation? I is equal to, no, not m, not q. I is equal to 1 to n, okay, where n is the training set. Okay, I mean I now understand that why you said q, because earlier I was taking the training set to be I is equal to 1 to q. So, in fact, in that sense you are right, but now I mean you should have been attentive in finding out that in this case we have defined the training set as I is equal to 1 to n. So, it is this capital N for which we have to do this summation. Now, realizing the cost function like this, okay, can be interpreted as follows. That means to say what? That you have got totally capital N number of training samples, and you are adding up the squared error of all these training samples, and then combinedly you are getting a single index, single cost function C, okay, which is being represented like this. And what you are going to do now in order to reduce the, I mean in order to reduce the error, you must now take a derivative of this CW with respect to W, and then you will adjust the weights. You did it earlier also, okay, but in earlier case we were feeding each and every example we were giving. I mean here we have a training set, okay, and a training set means there are n number of examples already. In earlier case what we were doing, feed one example and then adjust the weight, feed the next example, adjust the weight, and so on. That means to say that by feeding n different examples, okay, we would have adjusted the weight n number of times. Whereas in this case, in this sort of a representation, what we are doing is that we are accumulating the sum of square errors, okay, for all the n examples which are there in the set, and once this n examples are all presented and we have accumulated the sum of square error, then we are going to adjust the weights. Okay. So, this CW is a combined cost function for all these patterns put together. All right. So, this means to say that this one, I mean, what sort of learning can we tell this? As a batch learning. This is a learning by batch. Okay. You feed all the n examples and then you adjust at the end. Whereas, the earlier learning what we discussed, presenting one sample and then adjusting the weight, again next sample, again adjusting the weight, that could be called as an online learning, whereas this one can be called as a batch learning. Okay. So, let this be the batch learning expression. Okay. Now, what we are going to do, okay, here we are getting only the error between di and f, but our objective is to get an expression where we have a relation between fx or error between fx and this f. Okay. So, we have to reach there. So, it is not very difficult to obtain that. So, before we do that, again some definitions that we have to some things which we have to define. Okay. Let us say that ET, okay, is the, when we write it is like this. Okay. This we are defining as the average operator over the entire training sample. So, this is, so when I write as ET within third bracket something, this is nothing but the average expectation, this is nothing but the average operator over entire training samples. Okay. The training samples is T, and that is why we have given E suffix T, and writing this as E suffix T is different from that of writing as the E operator directly. Okay. What is the E operator? E operator is nothing but it is the average over the whole ensemble of random variables. Whole ensemble of random variables. What are the random variables which are under consideration? X and D. Okay. So, there is a difference between calling it as E and calling it as ET, because ET is defined over the training samples, and in fact training sample is nothing but a subset of the ensemble. Okay. And another thing, that here we have been calling it as f x comma w. Okay. And after all, what is w indicating? In this kind of an empirical knowledge representation, w is actually an encoded form of the training that you are giving. So, we can, instead of writing it as xi comma w, we could also write, or rather f x comma w could be interchangeably written as f x comma t. Okay, where T is nothing but again the set of training samples. Okay. So, with that we can write down the cost function as follows, that we can say that CW, all right, is equal to half of, again the half is coming because of this. Okay. Now, mind you, what we are doing, that we are adding up all these things. Okay. But okay, leaving aside, we can add up and then we can divide it by n. So, some normalizing factor n if we consider over here, in that case this will represent nothing but the average squared error over the training samples, is not it? If we simply say that, if we simply define a quantity as 1 by n, I mean normalized by n, 1 by n CW, then it becomes nothing but half into 1 by n into this, and 1 by n into this is nothing but the average cost function. So, that means to say that the average of this square error, and this average of square error. So, we can represent CW in terms of the average of the square error as follows. So, here this average is over the training samples, that is the set of training samples. So, it is average E over T. Okay. So, here this thing we can represent as ET D minus F, okay, x vector comma T, because I have already said that instead of x vector comma W vector I could interchangeably write it as x vector comma T. So, this thing square I can write that, only thing is that I did not consider that 1 by n multiplication, that is implied. So, this is the way whereby the cost function could be represented. Now, we have to calculate this average of this quantity. Now, average of this quantity can be calculated in an easier way as follows, that let us see that what is the argument of this, it is d minus f of this function. So, d minus f of x vector t, okay, this could be written as d minus f x vector plus f x vector minus f x vector t. Okay. Just I added one fx and I subtracted one fx, nothing more than that. Okay. Now, let us interpret this. What is d minus fx? D minus fx is epsilon. So, it is epsilon plus what is this, fx minus fx comma tau. In fact, this is what we are looking for, the error between the actual function, or rather the regression function, and the approximation that we are doing by applying the neural network. So, this is this is epsilon plus f of x vector minus f capital F of x vector t. All right. So, now if I substitute this, so instead of d minus f x comma t, if I substitute this expression into this, all right, into the expression for CW, in that case what do we get for CW? We are getting CW is equal to, you can just see, instead of d minus f we are going to write as epsilon plus fx minus fx tau, okay, and that leads to many quantities. Okay, that leads to, in fact, it is this plus this whole square form. So, there will be a term which will be written as E t, half of E t epsilon square, yes, very much, epsilon square term will be there, plus there will be another term which will be half of E t, okay, and square of this quantity, that is to say f x vector minus f x vector t, this whole square, okay, this quantity, and then there will be another term which will be epsilon times this, and I can easily hear that some of the students have already said that this is going to be equal to 0. So, why this is equal to 0? I think for those who haven't understood, we can have a brief discussion in the next part, because time is running out for today. So, let us just complete this expression, okay, and in the next class we will continue from this point. So, this is x vector comma t, all right. So, this is the expansion of this one that we are getting. So, this one is a term to be considered, this one is a term to be considered, and this one some students have felt that this should be equal to 0, and why, that one we will see in the next class. So, till then, goodbye. Thank you.